So today's session is on Powertrain Sizing Simulations for Student Racing Teams by Venugopal of Decibel Labs. In this session, Venugopal will address the approach and detailed studies needed to finalize and optimize component sizing for various loads, driver behaviors, weight targets, pack sizing optimizations, and more. So, a bit about Venugopal. He's the team member of Electric Formula Student Team at KTH Sweden. He's engaged in powertrain simulation studies for the development of the electric Formula Student car. He's also the CTO at Decibels Lab, engaged in the development of advanced powertrain models for component sizing, optimization, auxiliary load estimations, thermal estimation for passenger and commercial vehicle segment. And Venue has also worked on activities such as cell testing, characterization, model-based design for SOC, SOH, and cell balancing. So without further ado, please let me invite Venugopal to the front screen. Venugopal, please go ahead.
Yep. Thank you. Thank you so much for the intro. And yeah, once again, I welcome everyone to the session. I hope I am audible to everyone and you all can see my screen.
Yes,
So
both
without
good.
waiting, we can start the session. So yeah, today's main session is on powertrain sizing simulations for student racing teams. So yeah, about myself, I'm just Venugopal, currently pursuing my master's in KTH Royal Institute of Technology. And yeah, I'm working on like powertrain simulations. I have expertise in like model-based design of electric vehicle powertrains, hybrid electric vehicle powertrains, as well as have been working on developing the simulation models for lithium-ion cell, BMS algorithms, and I also got the opportunity to test the cells which are used for like formula applications. So here you can see the equipment which I'm working on, the industry graded equipment are being, so where I have tested the formula cells, and yeah, I'm developing some simulation models for understanding the cell characteristics and the stuff. So basically today we are going to discuss regarding the powertrain simulations, which will help you out in sizing the components, mainly like the powertrain components. So without waiting, we'll start with the session. So yeah, we all know what is the main purpose of powertrain simulations. So the main purpose of doing these powertrain simulations, well, like there are many reasons, but all these can be categorized and can be named as component sizing and for energy optimization. So there are like many components. Let's say like wheel to well. So there are like many components: wheels, differentials, motors, gearbox, inverters, as well as like the battery pack. There are like many components, so we have to size them. Sizing here in the sense like not in the design terms, but in terms of like energy or like the performance or in terms of like efficiency. So we'll be mainly talking in those terms, not in terms of like design or CAD models. Okay, and optimizing those components to get like a more efficient, to make them work more efficient. So what are the other purposes, or like what are the subcategories of this component sizing and energy optimization work? So one of the first parameter is like identifying the performance requirements. So we all will be developing a car, and the main aim of developing the car is we have to reach some standards, or like we have to reach some performance that was set up by the event. Okay, so first we have to identify the performance requirements, and then we have to go with like these powertrain simulations. So we can do like wheel to well analysis and well to wheel analysis. So basically the wheel to well analysis is said to be like sizing, and the well to wheel analysis is said to be like the performance analysis. And the third one is like estimating the vehicle resistive forces. So here basically we are having like different types of resistive forces which will be acting on the vehicle, and these are the main reason which leads to like a consumption of more energy, or which also make you like stands in the some, not in the first position, or like makes you stand in somewhere in the queue when you're going for the race events. So we have to study mainly these vehicle resistive forces. And the other thing is like get the gear ratio, which plays a very important role in like energy consumption. I hope if you have done like gear ratio versus energy consumption, then you might have got like some good results. So please do that. It will help you out in giving you like a clarity like how the gear ratio is affecting the energy consumption. And the next one is like determining the motor size in terms of torque, RPM, power, voltage, and current. So basically, what in real time what will happen is like we'll select some motor or like some events will give you like this is the motor, this is the battery pack. You implement these two and develop the vehicle. But the other way around will be like they will tell you like whatever the motor you choose it's up to you, but come up with like these kind of performance requirements and all the stuff. So they in that point of view these powertrain simulations will help you a lot. So with this outcomes of this determining the motor size, you can select your own motor and you can go for building the vehicle. And finally we can size your battery pack in terms of voltage, current, energy, or like C rates or yeah, mass and all the stuff. Okay. And we can estimate like energy consumption. Yes, we have the event called energy efficient event in the formula events, right? So if your vehicle is consuming less energy, which means like your vehicle is more efficient. So if you want to understand before going to the real time testing of the vehicle, then you can develop this powertrain simulation and you can estimate your energy consumption of the vehicle. And finally the range estimation. Yeah, this is not that prior goal for like a formula event, but it is very important because there are like we have to complete this many number of labs, let's say like 18 labs. So then when we are estimating the battery pack size, then we have to estimate like the distance the vehicle has to travel. So that's where like the range estimation will come into picture, and through this powertrain simulations we can understand that particular point also. So other things were like auxiliary system modeling, which is mainly the motor cooling and battery cooling. We all know that we'll be running the vehicle at like higher speeds, right? So in order to cool the, I mean like in order to reach those speeds, the motor will be like always running at higher RPMs. So in order to make the motor work in best efficient region, so it's better to go for like active cooling. So if you are going with active cooling, then we have to provide some energy for the pump and all the stuff, so we have to consider those energy consumption also. So in this powertrain simulation model we can consider those active cooling for motor and battery. And yeah, finally how the driver behavior is affecting the energy consumption or the battery pack size. Okay, so those things also we can include in this powertrain simulation. So these are the main reasons why we are going with the powertrain simulations, and yeah, these things will help you out in developing a really good efficient car. So now up to now we have discussed like what are the purposes, but what are the parameters that we have to consider while developing the powertrain simulations. Okay, so there are like general targets which I'm not going to discuss about those things, but we have to mainly focus on technical targets. Okay, general targets will be like for the commercial vehicles, but we are not going for the commercial vehicles as we are mainly focused towards race cars. So I'll mainly focus on these technical targets. One is like low weight of the vehicle. Yeah, in our event we are having like a weight competition, so the lesser the weight you'll get like more points. And apart from that, we have to think about like why we have to go with the low weight of the vehicle. So it directly implies low weight of the pack. Okay, which means like we have to have low pack, then only we can have like pack here in the sense like battery pack. So that's the only heavy component that we can, individual component. So that's the reason like I specifically mentioned that low weight of the pack will give like low weight of the vehicle. And the high torque implies like a high current from the pack. When you want like initial accelerations to be very high, then your pack current should be very high. And also like maximum speeds, so it again depends upon like how much voltage you are getting from the battery pack. Peak acceleration performance depends upon like peak discharge currents. And gradability. So yeah, unfortunately, I mean like in the formula race car events, we won't be having any gradability, but so we can give it as like a 0 degree. But if you are feel like you have to give a little bit of gradability, yeah, you're always welcome to give a little bit so that you are oversizing the battery pack. So if something goes wrong, you'll be on the safe side. Okay. And then another one is like a mileage, range, and other if any. Like we have to consider all these performance characteristics before going for like developing these powertrain simulations. Okay, so I'm telling you like as I have experienced all these things, I'm telling you all these things. But as an engineer who is going to work on developing a vehicle, So the only way is how we can analyze all these things is by doing the powertrain simulations or real-time vehicle testing. So is it good to go with powertrain simulations or real-time vehicle testing? So the real-time vehicle testing will take a lot of time to develop the vehicle. Okay, so we have to invest a lot of time and also like financial. So it's not that feasible, right? So that's the reason it's better to go with powertrain simulations, analyze the vehicle in your simulations, and then go for building the vehicle. So that's why like we'll start with the powertrain simulations. Okay, so now we have looked like what are the characteristics that we have to look up. So before that, I mean, like after considering the characteristics, we also have to do some data analysis, which means like we have to compare the data of the previous events and from the previous vehicles. So I have done like a little bit of analysis for you guys over here. So if you look at over here, the first table here, it's showing the energy consumptions and the teams and the years here. Okay, so in the year 2019, 2018, 17, 16, these are the six teams, top six teams I'm taking over here for analysis. So the team one, the energy consumption is like 4.47 kilowatt hour, whereas the sixth team is consuming like 6.186 kilowatt hour. And similarly, year two, year three, and year four. So you also have to do is like it's better to check the previous 4 years. What is the energy consumption that is taken by like the first vehicle or the winner? So we always have to target that value. So because we always want to be on the top list, right? So we always have to target for like 4.474, or you can keep like top five or like top three. It's up to the team targets. So every team will be having like their own targets. So then another like some other teams over here like it's just like in general data. Then we have to look for like same vehicle parameters. Maybe some other team will be having like a same vehicle structure as ours. It might be like they might be using same motors as of ours, they might be using same battery pack size and similar masses or something like that. So then we have to evaluate like how much of energy consumption and how much of time the vehicle is running for. So if you look at over here, I mentioned the times also. So the energy consumption is like 6.77 kilowatt hour for 1626 seconds, and the mass is like 240 kgs. This is in the 2019, 2018, and 2017. So after doing all this analysis, so I concluded that to be in top six, the energy consumption should be less than 6.2 kilowatt hour. Okay, so for that, for my vehicle, Team A is my vehicle, which means like it's all our vehicles. Okay, so energy consumption, I have developed like the energy consumption or like the powertrain simulations for like four drivers. One is like a lap time simulation driver, normal driver, and a race driver with 90 percentage, and a race driver with a full capacity. So when we are going with lap time simulations, we are getting energy consumption of around like 7.485 kilowatt hour, whereas when we are going with like a race driver with the full capabilities, it's coming around like 6.913. Okay, so and the vehicle weight is like 240 kilograms, and the time is like 1560 or like 1620. It's around like 18 to 19 laps of race event. This is like without region again, and with region also we have to think of. So with region I'm coming with around like 6.13 and 5.397. So then I can go with like if you're 100% sure that you can region the or recuperate the energy from the braking events, then you can go with like a region, or otherwise you can go with like without region, and you can set your limits. Okay, so this what you have to do before like developing the simulation, and this is your consideration or like the target. Okay, I have to reach 6 kilowatt of battery pack size. So how I can reach that 6 kilowatt of battery pack size? So there are many things which you have to do. One is like analyzing the resistive forces, and also we have to do like energy consumption versus drag coefficient values, and energy consumption versus rolling resistance values, and also energy consumption versus the frontal area values. Okay, this all depends upon like aerodynamic forces and all this stuff. Okay, so for that we are going to do like the first performance analysis, which is from wheel to well analysis. So in this what we are going to do is like we'll be giving drive cycle as input. So drive cycle is nothing but your velocity versus time data. So this will be giving as input, and we'll try to estimate wheel RPM, wheel torque at each and every second of time. Okay. So through hand calculations, we can do all these things. But the thing is, like when you're doing in the hand calculations, we can do at a singular point of time. Okay, but it is always suggested to analyze the calculations at each and every second of time, so that we'll get to know like what is the peak rpm we are reaching, or like what is the peak torques that the vehicle is expecting. Okay, so through these simulations we can estimate like a wheel rpms on top, and also we can estimate like vehicle resistive forces. So at each and every second of time, so your track might will be having like something like circular track, so the resistive forces will not always same at each and every point. So that what we can do is like we can estimate the resistive forces such as rolling resistance force, the grade resistance, aerodynamic force, and the inertial force at each and every second of time. Okay, so after calculating these things, we can transfer these forces onto the motor side, and we can size our motor. Okay, I'll come to that. So before that, we are having like a small component over here, that is gearbox. Okay, which will be directly coupled with the motors. It's up to the strategy you're following, or like the motors you're selecting. Okay, so when you're selecting like particular gear ratio, I would suggest you go with like start selecting the gear ratio from like, let's say like 1, and go up to like 20 values. Okay, so you'll get like try to plot this plot, gear ratio versus energy consumption. Okay, so when the gear ratio is 1, you might be having like a high energy consumption. So like this you'll be getting, and this will go something like this. So at particular gear ratio, you'll be having like a low energy consumption. Okay, and you can also observe gear ratio versus the transmission efficiency, and also we can observe gear ratio versus the motor efficiency. Okay, so let's say like we are getting at a gear ratio of 10, we are getting low energy consumption, and here if we are getting like somewhere around 8, we are getting highest transmission efficiency. And here, let's say you are getting around like here 11, at gear ratio of 11, you are getting like a max motor efficiency. So then think of like which parameter is important for you, either energy consumption, or like the transmission of the gearbox, efficiency of the transmission, or like the motor efficiency. So try to take a decision out there, and move ahead with like gear ratios. Okay, so as we are developing the vehicle for the race events, and it is will be like for like one time or two times, so then I would suggest like always the energy consumption. If it is like commercial vehicles, then we have to think about like life cycle of the components, then we can go with this kind of analysis. Okay, so all these things can be studied in this powertrain simulations. Now I'll try to show you like some graphical data that you'll be getting from the powertrain simulations. So this is the Formula Student Germany track velocity profile. So if you give this velocity profile as input, so these are all the outputs we are getting over here. So the first one is like the rolling resistance. We all know it's because of the tires and in the contact between the road. So it's maintaining the constant throughout the drive cycle. We can make it independent, dependent of drive cycle also, which means like a function of velocity. When the velocity crosses this much, let's say like 30 kmph or something like that, we can make it dependent of velocity like that. Okay, it's up to you to what accurate level you want to develop the models. And next one is like grade resistance. I have taken it over here as like 0. There is, which means like the road is flat. And next one is like aerodynamic force. So it is nothing but half rho cd av square. And this is like one of the biggest energy consumption parameter, because the race cars will be always running at like a very higher speeds. So at higher speeds, let's say like this is our formula, half rho cd av square. So v square term is there, right? So your velocity will be drastically increasing, and you'll be getting like more resistive force here. Okay, and this is like a acceleration force, and this is the total resistive force at each and every second of time. So we can calculate from this resistive force like the rpms and torques. So torque is nothing but like the force acting on the wheel into perpendicular distance, which is nothing but the wheel radius. So that can be visualized over here. This is the wheel torque, and this is like wheel rpm. Okay, and another analysis that can be done over here is like what's happening when you are changing the radius of the tire, and also width of the tires. Okay, so because like the torque can be minimized or maximized by varying the radius of the tires. Okay, so that analysis can also be done over here. Apart from that, these are like the energy consumptions during the acceleration, and this is the regenerative energy available somewhere around like 1.5. These are on like vehicle side. Okay, I have divided like whole powertrain into three parts. One is like before motor, motor, and after motor. okay, which is nothing but the battery pack. So before motor, this is the energy that vehicle can give you back, which means like the regen energy, which is around approximately 1.8 kilowatt hour, and this is the energy that the vehicle is expecting, around 6 point or like 5.8 kilowatt hour. Okay, so then we have to go for like a motor. So the motor will be asking you for like some of the inputs. Mainly, it will ask you like the motor RPM that you are expecting at each and every second, and the motor torque. Okay, so those two things will be giving it as inputs, and we'll try to calculate the motor parameters, and we also evaluate like motor performance characteristics. So from this we can estimate like the motor torque at each and every second of time. So based on that, you'll be getting some graphs, and we can from the graphical data we have to do some analysis. Okay, what is the peak torque that the motor is giving, and what is the nominal torque? So based on that we can select like motor torque ratings, continuous and peak values, and we can go for like a particular vendor who is selling this kind of motors, and you can select your motors. And similarly the motor RPM rating, power ratings. Okay, so these are like mechanical terms, but we have to look into like voltage terms also, because we are having restrictions. Either we have to go with like 48 volt or like 60 volts or 96 volts or 600 volt. Okay, so different events will be having like different voltage. So that's the reason whatever the RPMs we are getting over here, we'll try to convert them onto like the voltages, basically using like some equivalent circuit equations of motors, or like back EMF constants and torque constants. So if you're using the back EMF constant, you can convert like RPM of the motor to like the voltage, and if you're using the torque constant, you can convert the torque to the currents. And we can also estimate the efficiency. So how we can estimate this efficiency is a little bit a difficult task, but the good thing is like after estimating these parameters, you can go for like market research or like market analysis, who is selling this kind of motors and stuff, and you can ask them for like the motor data sheets. Okay, with that, along with the motor data sheets, they can give you like the efficiency map of that particular motor. Okay, so you can directly implement that, or sometimes you can go with like your constant efficiency like 85 percentage, or like around 90%, something like that. Okay, so if you know the exact efficiency map, we can estimate like the motor losses, and if you're estimating the motor losses, it's nothing but like the losses always be in terms of heat. So because of that heat, the temperature will be developed, and we can estimate like the temperature. And if once we are having the temperature, the motor will go into like a bad efficiency regions. So in order to bring it back to the nominal operating regions, we have to provide some kind of cooling. So that's where we'll go for like motor cooling. So again, in cooling, there are like two things: active and passive coolings. Okay, so it's up to us like how we want to develop the cooling part of the motors and batteries. So these are the things that we can study in the powertrain simulations. And yeah, these are some of the results which we'll be getting from like the powertrain simulations. Here, what I've done is like after converting the wheel RPM and wheel torque, I multiplied them with like gear ratios and divide them with gear ratios. Okay, to convert the motor to get like a motor RPM and motor torque, and then I have calculated like motor power, and using the back EMF constant, torque constant, I converted like motor voltage. So if you look at over here, we can understand like at each and every second what is the voltage that the motor is expecting. And we can also see here like sometimes here I have plotted only the positive voltage variations. Okay, we can look at like negative voltage variations, which means the region. Okay, I mean, like it's only the directional change. It's not the voltage. Only it's negative in the sense like it's just the directional change. Okay. And next one is like efficiency. It's always varying in between like 0.78 to like 0.88. So this is the max efficiency that the motor that it is giving for that particular drive cycle. So all these things can be studied using this powertrain simulations. So now we are done with like motor part. We can move forward to like the battery pack part. Okay, yeah, before moving to battery, we can also see here like this very important plot. Okay, so these are like operating points, which are nothing but your velocity versus time points. At each and every second, you will be needing like some torque, and you will be having some RPM, whereas this green line indicates your motor torque versus a speed curve, or like power curve, whatever it might be. It is like a max torque region, and this is like a power region, and this is like a max RPM region. Okay, so if you try to plot this operating points, so that we'll get to understand that okay, where your operating motor. So from this image we can understand the motor is almost operated in the like max torque region and at higher speeds. Okay, so similarly this for like a particularly different application, but for your case you can plot like this and you can understand where exactly you're operating the motor. Okay, and you can also plot the efficiency map along with this. In this your efficiency maps will be something like this. Sorry, both are like red in color. Yeah, let's say like this is like 90 percentage, 85 percentage, 80 percentage, 75 percentage, like this. So you'll get to know, okay, I'm operating most of the points in 75% region. So how I can move these operating points to 90% region. Okay, so it can be either by varying the voltage at currents, or like either by varying the gear ratios. Okay, you can do all those analysis using this particular simulation part. So finally, after doing all those things, we'll be getting like a motor voltage, motor current, and motor power in electrical terms. Okay. So in between motor and battery, there is another person who will be sitting. So inverter. So this will be like AC signals, and here the battery will be like a DC source. So this will be converting to AC to the DC and DC to the AC. Inverters and converters will be using. So we have to include the efficiency map of this inverter, so that we can directly convert this power on the motor side to like power on the battery side. So if once you get the power on the battery side, we can estimate like what is the battery voltage, what is the battery current, what is the battery pack energy, because like it's just integration of power is nothing but energy. Okay, so these are all the things that we can estimate from this particular simulation. One is like battery current ratings. So in battery mainly we have to think about like nominal, continuous, and peak, whereas in motors we'll be having only two or like three also there sometimes, nominal, continuous, and peak. But in batteries we always have to think about three values: what is your nominal current ratings, what is your continuous, and what is your peak. Okay, because nominal we always will go with like a nominal values to be on the safe side, and the continuous values will determine continuous torque and continuous RPM of the motor. Okay, and peak values will determine your peak torque and peak performance and peak accelerations of the vehicle. So that's the reason these are very very important. And also like a battery voltage regions ratings, again here we'll be having like a nominal, continuous, and peak. So these are very important because we in batteries will be having like a over voltage, nominal voltage, and under voltage limits. So we always have to operate the battery in between these limits. Okay, so that's how we'll be implementing these things, and we can analyze these three things also. Battery power rating. So in order to get like continuous power, there has to be some continuous ratings of the currents. So here also we'll be having continuous and peak. Charge and discharge efficiency. So basically for lithium ion cells, mostly we'll be taking as like one as efficiencies, but the thing is like as we are operating very dynamic, so the charge and discharge efficiencies will be very less. So we have to go with like 98% or like 97 percentage, as it is like a dynamic profile. Okay, and from this efficiencies we can estimate the losses, I square losses and stuff. So again it leads like the temperature development and cooling, active passive coolings. And the important thing is like a BMS part. So if you know like what is the amount of current that you are discharging and how the voltage is behaving, so then we can estimate the state of charge. So if you know the state of charge, you can know like how much energy is left out in the battery pack, and how far the vehicle, or like how many laps still the vehicle can give you. So those things we can analyze. And battery voltage behavior, which means like we can operate the battery in between like 90 to 10 percentage. Basically we'll follow this rule for like commercial vehicles, but for race applications, yeah, we are not much focusing on like battery life, so we can operate in between like 100 to 0 percentage. But the thing is, we have to develop some SOC strategy. If you're going with like 100 to 0 percentage, so there has to be some SOC strategy that we have to go with. I'll discuss regarding the SOC strategy in the coming slides. Okay, but yeah, so once after doing all these things, you also will get like how many number of cells were connected in series, how many number of cells were connected in parallel, total number of cells, battery pack mass, everything will be coming from this particular simulation. So if you observe like these three things, one is on the vehicle, motor and battery. The only input we are giving is vehicle parameters, which is nothing but like vehicle mass and the rolling resistance coefficient of the tires and the radius of the tires, okay, and also like aerodynamic coefficients and the drive cycle. These are the important inputs we are giving, but as outputs we are getting like many parameters, okay, whether either it might be on the vehicle side, motor side, or battery side. So yeah, there are some of the results that I got in the powertrain simulations on the battery side. So you can see here like this is the battery current variation at each and every second, and this is the power input and the power output. Power input and power output is nothing but like this is the battery that is delivered by the battery pack to the motor. So if you subtract these two things, we'll be getting like the losses, which is nothing but you can see over here. So if you this is nothing but the loss, you can develop some temperature because of this losses Q equal to mcp delta T, and we can estimate the temperature development and we can go for cooling. And these are like discharge energy and charge energy. So if you remember, when we are looking only on the vehicle side, we got like somewhere around 5.8, but here it is going around like approximately 7.2 kilowatt hour. Why it has been increased from 5.8 to 7.2? Okay, it's almost like 1.4 kilowatt hour of extra energy. So there are many losses that were happening in between these things. One is like on the transmission, and next one is like on the motor side we are having losses, and on the inverter side we are having losses, and the fourth one in the battery pack also we are having losses. Okay, so without considering all these losses, if you go directly with like 5.8, then what will happen is like you will end up in the middle of the race event. Okay, so that's the reason we have to analyze each and every component, and then only we have to select the, okay, this is the my battery pack size. And also if you look at over here, we are getting charge energy somewhere around like 2.2 kilowatt hour. Okay, but are we sure can we recuperate 2.2 kilowatt hour, whether we are having that technology developed in our vehicle to recuperate 2.2 kilowatt hour? So we have to think of those points, and then only we can go for 7.2 minus 2.2, which is like a 5 kilowatt battery pack. If you are not sure, then we should not go with like 2.2 kilowatt hour. We can go with like 1 kilowatt hour on the safe side. Okay, so we can go with the 6 kilowatt. So these things you have to do like so many number of iterations of simulations, then only you can analyze this data, and you'll get to conclusion, okay, this is the value which I can go with, something like that. So now I'll try to show the model. So this is the model, powertrain simulation model. So I'll try to explain each and every block over here. So this is the profile, velocity profile, which is nothing but the formula student Germany student track. Okay, so Germany track I'm giving over here, which is nothing but the time versus velocity data that I'm giving as input. And if you integrate this, and you'll get like the distance. So sorry, I'm multiplying this like 18 times, you'll get like a different distance if you have to divide by 18 here. Okay, so in this what I'm going to do is like I am using some basic equations like the rolling distance equation, which is nothing but gross vehicle weight into CRR, and grade resistance, which is nothing but gross vehicle weight into sine theta, and the aerodynamic force of rho CdAv square. So basically, I'll use these equations and I'll try to convert everything, the velocity profile into like wheel torque and wheel RPMs and the powers, energies and everything. And then I'll give these things as inputs to the motor as motor torque and motor RPM. So in this again, I'll do some kind of conversions, electrical conversions. Okay, some because like these are like mechanical values, and we have to convert them to like a voltage and current. So there is like a equivalent model where we can convert this torque RPM to the voltage and currents. Okay, so after converting them, then I'll pass them to the battery pack over here as inputs as battery power and battery current. So here also we'll be doing like some kind of calculations. Okay, very small equations, but I mean like this throughout this model we'll be finding out like so many equations, but you might have come across these equations somewhere in your courses, or like when you're using or when you're doing some calculations. But the thing is how we can combine all these equations such that we'll get like a exact or like a the vehicle parameters. That's the important thing. Okay, so yeah, from this we are getting like a number of cells connected in series, parallel, pack mass, number of total cells, required battery current, and the total energy required. So if you look at over here, I'm getting like a 7.38 kilowatt of energy, and this is like capacity 13.67. Okay, so now here we know 7.38 kilowatt hour, and we know capacity, which is nothing but amp hour. So if you divide these two things, you'll get like voltage of the battery pack. Okay, that's the one thing. And if you know like capacity is 13.67, then you can estimate like how many number of cells you have to connect in parallel. Okay, because like if here I'm selecting like 6.6 amp hour cell for my application, you might be selecting like a 5 amp hour cell or like 2 amp hour cell. I'll discuss like how to go for the cell selection also. So you'll be selecting the cells, and based on that you'll get like number of cells connected in parallel and series. Okay, and if you multiply these two, you'll get like total number of cells, and you'll be having like a cell mass which is defined by the cell manufacturer. So if you multiply with that, you'll get like a battery pack mass. Okay, so this what we are getting, and this is like a regenerative strategy. Okay, so in the regenerative strategy, we also have to think about like how much uh, current the cell can take and all these things. So based on that, we have to give some torque limits on the braking side, and also like we, as I told you, like we have to discuss about like SOC strategy, which means like from where we have to discharge the cell, either from 100 percentage or from 95 percentage. Because if there are like initially in your dry cycle, if you're having continuous discharge until like let's say 100 seconds, then it's not a problem. But if there is like instant charge also, which means like after starting the vehicle from zero condition, there is a discharge, and if there is like a sudden charging case also, then what will happen is like this will give an error message to the BMS saying that you are reaching the over voltage limit. So that's the reason we have to go with some limits over there. And yeah, so if you look at over here, you are getting some regenerative energy that we can recuperate along with these limits and stuff. So this is the overall model. But one thing over here is like I haven't considered the torque vectoring. So because like the torque vectoring also plays a very important role in these race events, as we are having like a circular race tracks. So I mean like the wheels will not always be running at the same speed. So when we're taking like right turn and left turns, the wheel RPMs will be changing, which means like the torque also will be changing from the right side wheels to the left side wheels. So we have to include the torque vectoring model also. But yeah, it's up to you guys like whether we can implement that it or not. But yeah, it will be great if you can implement it. So this is like the powertrain simulation model, including the torque vectoring model. So here what we have done is like we have taken the each wheel's RPMs, or like each wheel's power, and then calculate like energy consumption. Okay, it will result in some uh, extra energy consumption or like low energy consumption, because when one wheel is running at higher RPMs, it will be needing like a low torque. So that operating point might be in the bad efficiency region. We don't know. So in order to analyze all these things, it is suggestible to like go with like a torque vectoring model also. Okay, so yeah, and this is the powertrain simulation auxiliary model, only for like battery and motor. So first what I will do is like I will estimate the motor temperature, and I will give this to like a if block, so we can operate the motor in between two temperature regions. Either it might be like here I get given it as like a 293 to 350 Kelvin. So whenever it is going out of these regions, okay, so then I have to send some coolant to the motor, and what amount of coolant I have to send. So all those things will be taken by this action subsystem. I'll define all those parameters like so let's say like if my temperature is going around 350 Kelvin, above 350, then let's say like I want to send X amount of cooling and coolant. So that what it will do is like initially your temperature will be, this is 293, it will be increasing to like 350, and again it will tries to bring it back. So it will follow something like this. So these for only active cooling, which means you are controlling the coolant pump or like the radiator and all the stuff. If you are going with the passive cooling, so which means like will be our pump will be always on, and you'll be continuously sending the coolant. But the disadvantage compared to the active cooling is continuously we have to supply energy for this particular pump. Okay, so if we can implement like an active cooling system, then we can decrease the energy consumption and we can save some energy and we can be on the like top in the energy efficiency event. Okay, and similarly this same thing can be developed for like the battery also, because everything is same, just like instead of temperature of the motor we'll be getting like the battery temperature, right? So now what I will do is like I'll try to show the model which I have developed in the MATLAB, so that might give you like some clear idea. So yeah, this is the code, and I'm loading the drive cycle over here, which I told you like the German track. And as I told you, like we have done for like a different drive cycles, race driver, normal driver, and all the things. So these are all the data files for that particular thing, and these are all like vehicle parameters, and these are like efficiency map for motors and efficiency map for inverters and all the stuff. If I run this particular thing, it has to give us some results. We'll see. So yeah, this is the model which we have discussed in the presentation. So this is the velocity, and this is the mechanical model. In this mechanical model, if you go inside this, so yeah, I have built like something like this, raised to force calculations, each and everything, like each and every parameter that what we have discussed, very small formulas, but how we are combining those things is like a very important thing. So we can combine all these things like this, and you can get like mainly the outputs as these things, and you can give these things as input to the motor, and in the motor also you can get like all these parameters. So yeah, I think we have already run this. I'll show you the graphs, the same graphs which I kept it in the presentation. So yeah, these are for like on the vehicle side, velocity, rolling distance, grade distance, resistive forces, and all the stuff. This is on the motor side, motor RPM, motor omega, motor torque. So you can also develop like different types of graphs from the data which you are getting from these powertrain simulations. Here I just plotted like omega versus time. So what you can do is like you can also plot omega versus torque, or like omega versus power and all the stuff, and you can analyze where exactly this operating point is going and all these things. It will be fun to understand the parameters and developing your vehicle. So yeah. So after developing all these models, next thing what you are doing is like you're getting some values over here. Then you'll go for like some cell selections, or like from the motor selection. Okay. So let's say here, yeah, this is the motor RPM. If you look at over here, it's going somewhere around like 18,000 as the peak RPM. Okay. So that is the RPM that is needed for the in the peak cases, like a high velocity ranges. Okay. So you can give a tolerance value of like a 5 to 10 percentage, and you can select like either 17,000 or like 16,000 RPM. And if you look at over here, you can find out the nominal RPM values also. Okay, so based on that you can ask your vendor, so this is my requirement, like 18,000 RPM is my peak RPM of the motor, and nominal value is somewhere around like 12,000 or like 10,000 RPM, and the torque value is coming somewhere around like 60 Newton meter approximately. That is the peak torque, and the nominal torque will be somewhere around like 30 Newton meter or like 28 Newton meter, something like that. And based on that you can select the your motor, and you can also select like your voltage ranges. So if you look at over here, the motor is expecting somewhere around like 300 or like 320 volts or sometimes 350 volts as the peak. Okay, whenever we have like touching like 18,000 RPM, it is touching like 350 RPM, sorry, 350 volts. Okay, so if the motor needs 350 volts, then how much DC voltage from the battery has to come? So all these things can be analyzed. Okay, so you can take the instant of this particular time, and you can look at like your battery side also, whether we are how much voltage the battery is giving. Okay, so I can show that graph also, battery side, what is the battery back voltage. Okay, I think I haven't kept it over here, but yeah, we are having battery current and we are having the power over here. If you divide these two, you'll get the voltage, and we can analyze like what is the voltage that the battery has to give at that point of time. Okay, so yeah, this is very good to analyze the data. Okay, so now after doing all these simulations, we have to go with like some cell selection. Okay, so here I'm getting like 13.67 amp hour, and somewhere around like 530 volts or like 540 volts is my requirement. So there we have to do some kind of calculations, pack calculations, which means like number of cells in series and parallel, like that. So here I'm getting 13.67, right? So what I can do is I can go with either 7 amp hour cell, so that if I connect two cells in parallel, it will become like 14 amp hour. Okay, which means we are on the safe side in terms of energy. If you are going with like 7 amp hour cells, we are connecting two cells in parallel. So if you're connecting more cells in parallel, there will be losses, as well as like more number of components has to be added. So those kind of things will be there. Instead of that, you can go directly with 14 amp hour cell also. But you have to test like whether the 14 amp hour cell is giving the same performance as like 7 amp hour cell. If not, you can also go with like a 2 amp hour cells, or like 3 amp hour cells, 4 amp hour cells. But you have to do some kind of analysis. So I'll show you like what analysis you have to do. So what I've done is like now I got my requirements, what is the cell capacity I need and all the stuff. So I went for like a market survey for the motors as well as for the cell, but now I'm discussing only on the cells. So I have selected like different cells from the different manufacturers. So this is like Mingda, uh, their main supplies for the Formula cars, like a high power, high energy cells they are manufacturing. So from them, I have taken like this kind of cells. One is like 6.6, 12,000 and 12,500 mAh cells, and also other manufacturers such as like Malasta, E-Propulsions, and Energus. Okay, so five different companies. I have selected like different cells, like almost like 1,000 cells we have compared, and from all those things we have selected totally of six, and in this six finally we'll be using one after testing on all the stuff. Okay, but the main parameters that what we have to compare is energy densities. Okay, and the peak rates. Okay, so when you do the powertrain simulations, I have shown you some graphs, which means like the motor currents and the battery currents. So the battery currents, you can know like what is the battery peak current that is needed. So let's say like you need 200 amps. Okay, so here it is giving peak of 198 amps, which means we can go with this particular cell, but it's only giving like 198 amps. Okay, so like that we have to analyze. And if you come to like charge rates, it can take only 99 amps, but in your powertrain simulations, if you are getting like 150 amps, this cell can't take more than 99 amps. Okay, and continuously it can take only 63 amps. So based on all these parameters, you have to select your cell. And also important thing is mass. Okay, so here if you look at this particular, if I go with like 6.6, the battery pack is 35.17 kg. If I'm going with 12, I'm getting like 34.3. If I'm going with this, I'm getting like 36 kgs. But what is the energy required for the whole event in the sense like the endurance, the braking events, skid pad events, whatever you are having, you have to consider all those events. You have to sum up all the energies, and you have to say like, okay, this is the total energy required. Okay, so here if you look at the energy I am carrying with the battery pack is 7.327, and energy required is 6.95 kilowatt hour, which means extra energy of 0.377 kilowatt hour. So with this extra energy, we might be carrying extra mass. Okay, because we are connecting more number of cells, right? But how much extra mass we are carrying and how much extra energy it is, we have to bring a trade-off between that. Okay, if you look at over here, it is 34.3 kilograms, and it is like 0.25 kilowatt hour, and it is 36.56. And similarly other cells also 1.5 kilowatt hour extra. This is like so much of extra energy we are carrying. And this 0.74, 0.617, 0.49, these are like extra energy. So out of all these three, I can select like either 12 amp hour cell or like 6.5, 6.6 amp hour cell. Okay, so then we'll do some testing, and we'll validate the data with the data sheet that is provided by the manufacturer, and then we'll go for like battery pack building. Okay, so that's how these powertrain simulations will help you in battery pack building. And also that's how like the powertrain simulations will help you out in like selecting the motor based on the motor torque, motor current, and all the stuff. So this is like a SOC strategy, as I told you. Basically, like I told you, right? When you we can't continuously discharge the cell, so it depends upon the drive cycle. If you're having some events, let's say like a braking event, if you're directly going with the braking event, so what you will do is like initially you'll cruise the vehicle, so you're discharging the cell, and then you'll be applying the brakes. So you'll be applying like hard brake. So in this hard brake, you'll be getting like more amount of current. So then you have to look at like how much amount of energy is discharging and how much amount of energy we are getting because of this braking. So whether we can recuperate this much or not. So initially we have to think of all those things, and then we have to develop some strategies. And it also depends upon like the driver who is driving the vehicle, whether he is fully abusing the vehicle or like something like that. So if I'm going with like lap time data, lap time simulator, it is telling that it is good to start at 92.65. But when I'm starting with like a normal driver data, I can go with like 64. For race driver, it is like a 78 percentage, and for full driver, it is like a 88 percentage. Okay. So finally, we have to select a particular state of charge strategy, and we have to proceed with that. So yeah, there are some things that we can learn from this particular powertrain simulations. So, but where we can develop these powertrain simulations, everyone will be having the question like which softwares we have to use and all the things. So these are the some softwares which are available for developing these kind of simulations. One is like MATLAB. Uh, by coding, we can develop all these powertrain simulations. If we are good at like coding part, if you're not good at coding part, and if you know like mathematical equations, okay, then you can go with like Simulink and Simscape implementation. But I would always suggest like go with Simulink because it will give you like more knowledge in the sense like it will give you like a model based design, and it will give more clear cut idea how the particular component is working, or like how that gear ratio is working, or like how the motor is working. You can derive the equations and you can use those equations and stuff. Whereas in Simscape, what will happen is like you'll be having the differential, you'll be having the motor, you'll be having like a battery, you'll connect all those things. It's like plug and play kind of thing. It's good to analyze both the things. If you develop models in Simulink and Simscape, you can compare like the efficiency terms, which model is more accurate, or which is giving accuracy in terms of energy consumption and all this stuff. But in terms of learning purpose, I would always suggest go with like a Simulink. Okay, and the next software is like Scilab, which is having similar properties as a MATLAB. And Scilab is like a free open source software, and this is having like all functionalities which are very similar to like other softwares, MATLAB. Okay. Apart from this, we are having IPG CarMaker, Ricardo, Virtual Dynamics, Xmod, MSIM, and yeah, uh, we are having some other softwares also. Okay, but if you want to really understand the model based designs or like mathematical modeling, then you have to go with like either MATLAB or like Scilab. Okay, but yeah, I prefer like these two things. So after developing all these powertrain simulations, and after you're getting all this data, and you're like now in a good stage that okay, I got all the needful data that is needed for developing the vehicle. So what further you can do in terms of powertrain simulations? Okay, I won't say that powertrain simulations, but in powertrain, what more you can do in terms of motor or in terms of battery. So these are the some things which I want to bring it to you. So one thing is like validation of your sizing model. Okay, so in order to validate your sizing model, what you have to do is like you have to develop well to wheel analysis model, which means up to now we are giving input as a drive cycle, and we are getting like motor size, battery size, transmission, gear ratio, and all the stuff, energy consumption, and all the stuff. But now what we'll do is we'll give the battery pack size, and we'll give the motor parameters, and we'll give the drive cycle, and we'll ask the driver to accurately follow that drive cycle. Okay, which means like here we'll be implementing the driver model also. When we implement the driver model, it will make sure that the vehicle is following the drive cycle, and it will make sure that whether the energy, I mean like the battery pack size is sufficient or not. Okay, so in that ways we can validate the model. Or if not, you can directly go for like a real-time testing of the vehicle after developing the powertrain simulations. Okay, and coming to the battery motor side, what you can do is like you can develop in-depth model of motors. Okay, because formula teams means not only the one department, right? It's department of like many people will be working on electrical, electronics, mechanical. Everyone will be there, business and all the people. So if some electrical guys who are like more interested and understanding like how the machine is working and all the stuff, they can go in depth about like building the motor models and control models for the motor and all the stuff, and implement those things in this particular powertrain simulation model. And if some chemical engineering guys will be there who are responsible for developing the battery packs, so what they can do is like from these powertrain simulations we'll be getting like the cell, we can select like some cell. So then we can go for like testing the cell, doing some kind of test like pulse characterization test, or like impedance test, or like dynamic test, whatever the drive cycle you are giving to the powertrain simulation, you can give the same drive cycle to the cell also, and you can analyze how the cell is behaving in real time. Okay, so using that test data you can develop some kind of cell models, which is nothing but like cell characterization models, or like module characterization models, or pack level models, to understand like the battery behavior. And after that the major step is like developing your own BMS algorithms from the data that you're getting from these characterization models, as well as like the cell testing data. Using this you can develop your protection circuits, which means like voltage protection, current protection, temperature protections, and state of charge estimation using Kalman filters, or like state of health estimation, cell balancing. So you can develop your own algorithms, and you can implement those things in your controller, and you can implement that for your battery pack. Okay. So yeah, these are like further work after doing your powertrain simulations that you can done. Okay. So yeah, with this we are done with the session. Thank you so much. If you have any questions, I'll
Thank
try
you,
to
Venu.
answer those questions. Thank you so much.
So thanks, Venu. I've added the link to the Q&A in the chat box. Do you see it on the Zoom profile?
Yeah. Yes, I
Yeah.
can see that.
So if you open it, you should be able to see the. Just let me see once. All right, great. There you go. So we got a question from Hardik Srivastava. The negative voltage region will depict the braking or the deacceleration of the car. Um, I think that was this question. It was sent around half an hour ago. So I think at that point in time,
Yeah.
um, yeah.
Yes. Yeah. Exactly. Like the negative voltage here, it's just like the sign change. Okay, which means like it depicts the braking only, or like yeah, the deacceleration nothing but like we are applying some brakes, or we are slowing down the vehicle. So in that case only, like the motor will act as like a generator, and it will try to give you like region currents. So which means like if motor is rotating, then we can have like some voltage, right? So that's how we'll be getting like the voltage.
Okay, great. In the next question was from Abhishek. How can we estimate current draw by motor if no data is provided by the manufacturer?
uh, yeah, if no data is provided by the manufacturer, so then what you can do is like either you can go for some literature work of similar motor sizes in terms of like power ratings. Let's say like you, from your powertrain simulations, if you get like uh, a 6 kilowatt motor, then what you can do is like you can search from different vendors and different data sheets. So try to compare like their performance characteristics, whether they are having similar performance characteristics. So if they are accepting that, then you can take the motor torque constant and motor back EMF constant from those things, and you can convert those values. Or uh, if you're not getting that also, then what you can do is like you can develop your own machine model. Okay, so which is like more in depth of like for the electrical students, they can develop like own electrical model, and they can get like a KT and back EMF values. I think motorcad is a software they can use for getting these values and stuff. Yeah.
Sorry, I was on mute. The next question was from Sagar. I understood how you obtain the motor torque, RPM, and the voltage from simulations, but how did you obtain the desired efficiency for the motor? Won't we always desire 100% efficiency?
Yes. Yeah, we always will be designed for 100% efficiency, but the thing is like as I told you, the efficiency of the motor depends upon like many parameters. The major parameter will be like the gear ratio. Okay, I have given you an example also. The gear ratio will be affecting the energy consumption. It will be affecting the transmission efficiency, as well as it will be affecting the motor efficiency. If you are mainly focusing on the motor efficiency, let's say like we can do a small comparison over here. This is between the gear ratio versus motor efficiency. When gear ratio is like 10, you are getting like let's say like 75 percentage, and when gear ratio is like 18, you're getting like 88 percentage. When you're still going more than this, let's say like 24, you're getting like 90 percentage. Okay, so then we will be in like a dilemma, like which gear ratio we have to select, because here we are getting like a motor efficiency as more, but gear ratio is increasing. So this gear ratio might, as gear ratio increases, I told you like energy consumption will increase at some point of time. So we have to look into that. If energy consumption is not increasing, it still is in the decreasing mode. Okay, then in one way we can say that okay, we can go with this. But we have to also look at the transmission efficiency. If the transmission efficiency is decreasing, then we should not go with this value. We have to go with this particular thing. And the other point is, if you are increasing the gear ratio, which means like you're increasing your diameter of the gear ratio, diameter of the gearbox. Okay, so which means like you're indirectly increasing the components and the mass of the gearbox. And if you're going with like in-wheel motors, okay, if the gear ratio increases, the gearbox increases, and which means like it won't fit in the motor. So then we again, you have to increase your radius of the wheel. So like there are many cons also which you have to consider. So based on all these things, we have to think of like either we have to focus for 100 percentage, or are we satisfied with like 88 percentage. Okay, so yeah, that's how we have to take the decision, and we have to move forward.
Great. Venu, I think those are all our questions for today. Uh, if there's any, I've mentioned on the YouTube chat that if anyone has further questions, to contact you at contact@decibelslab.com. So thank you again for having this session with our teams. Really appreciate it on behalf of Formula Bharat. I wish you and the team at Decibels Lab the very best going ahead. Thanks again.